So we are looking at part B of experiment 7, and we have a particular chip here with the part number 74107. And there is some confusion with students between this chip and 7410. So I just wanted to mention this because I see this as a very common problem. Most people will have, well, all of you should have both the chips in your path kit 7410 as well as 74107. So you should look up the right chip part number and use that in this particular experiment. So on the left, we have the same JK flip-flop characteristic table that is being shown with the 4 different states of the JK flip-flop. And for clock input, we are just using P to indicate pulse, but we know that this is a negative edge triggered JK flip-flop because the clock input has a bubble in front of it. So pin number 12 on this chip is going to be the clock input, and it's going to be a negative edge triggered JK flip-flop. So we have, let's see, 4 inputs and 2 outputs. And my goal with this particular experiment is to uh, fill this table. So in order for me to fill this table, I need to look at Q before pulse. We were calling this Q previous. I need to set up J and K as 0, 1, and then go up and down with the clock to have a pulse in the clock input. And soon after that, I will try to observe Q and Q bar and fill out this truth table, fill out this characteristic table. So that's going to be my goal. And I'm going to set up things based on this chip. So there's no circuit here. We are just going to put the digital IO pins onto the respective pins of the JK flip-flop. So let's see. If I zoom in to U1A, which is 74107, I see that it belongs to the 7400 series ICs, which means that the first thing that I need to do is connect the power and ground. So the power needs to connect, or VCC, the 5-volt supply needs to be connected to pin number 14, and pin number 7 should be connected to ground. So if you look at the proto board here, you can see pin number 14. So I have a notch here, and there is a bubble at this edge, the bottom left, which indicates pin 1. So I'm like, if I go and counterclockwise, I have 1 through 7 and 8 through 14. So I've connected pin number 14 to, let me switch this on. Perhaps this is a better view. So I've connected pin number 14 to this top power rail, and it will become power rail once I connect it to plus 5 volts. And similarly, I've connected pin number 7 to ground rail. And once I connect the black wire from analog discovery to that rail, I have ground. So let me do that first, the power and the ground connections. So I'm going to take my analog discovery pin out. I'm going to put one red wire over there, and I'm going to take black wire because I have that color connected to the analog discovery ground, connected to the ground rail on the proto board. So that completes my power and ground connections to the proto board. The next thing is, let us try to see if we can go through and connect the inputs J, K, JK first. So what I'll do is I ideally want to have, so if I click on static IO in my waveforms window, I will also need supplies. So I'll have that window here as well. But if I look at static IO, what I have is 8, 9, 10, 11s and so on. I have 0 all the way to 7 in my, so I have 16 digital IO channels. And I could set them up as inputs or outputs depending on what my preference is. I have four of them over here. Just to make my life easy, what I'll do is I will switch on the show name um, option, and let's say because I have four of them, I will make channel 11J, I will make channel 10K, I will use channel 9 for CLK clock, and then I will use channel 8 for say clear CLR, and I also have a bar there because it's a active low input. So those are my four inputs. I've named them over here because it's very difficult to kind of monitor the digital I/O names. So that show name option is very helpful for particularly for this experiment. And then I have two outputs. So let's say Q, I will make that say for channel 0 I have Q bar, uh, and on channel 1 I have Q. So I'm using channel 11, 10, 9, 8 for inputs. I'm using channel 1 and 0 for outputs, the way I've shown here. So I'm going to have to connect those specific colors to my pins. So let's see, if I pull out J here, and don't be thrown off by the color of the wires. I'm connecting 0, which is digital channel 0 is pink color, and I'm connecting that to channel 0 was Q bar. Q bar was pin 2. So I'll connect this to pin 2 here. Next, I have channel 1, which in this case is a green wire. I need to connect that to um, Q. Q in the diagram is pin number 3 of the JK flip-flop. So I've connected that to pin number 3 here. So I've connected the two outputs accordingly. Next I have 8, 9, 10, 11. Let's start with 11. Uh, well, I can actually, doesn't really matter where I start. So I'm going to look at 8 here, and it can become a little bit confusing with the colors. So be careful about that. So 8 is pink stripe, and I'm going to connect that to uh, 8. 8 is clear bar. So pin 13. So pin 13 is all the way up there, just beside the, so just to see, I will give some room to the C. Next, I have say 9. 9 is the green stripe. The green stripe needs to be connected to 9. I've made 9 clock. Clock is pin number 12. So I'm going to connect this channel to pin number 12, which is right next to pin number 13. Next I have K, which is channel 10. Channel 10 is going to be purple stripe, and purple stripe is K, which means K is assigned to pin 4. So this goes to pin 4. So I've got 1, 2, 3, and 4 on the other side. And then the last input that I have is J, which is 11. 11 is brown stripe, and I'm going to connect that to J is connected to pin 1. So pin 1 of the IC is right there. And just for convenience, as you can see, I've used all the yellows for inputs and the greens at the very end, I've used them for outputs. Note that these are intermediate wires, not the same colors as the pinouts of analog discovery. These are just the intermediate ones that I'm using. All right, so I don't want this to sort of tilt. I just want this to be fixed here. I can lock the focus. All right, so I hope that you were able to see me connect the wires, set up the IC, and use the show name option in waveforms to select the J's and the K's and name those channels. So what we can do next is actually turn on supplies. So if I turn on supplies, well, I only need +5, so I'm going to go all the way up, turn on the 5, and I can now turn off the negative supply. I don't need that. So I have +5 right now on. If I go back to my static IO, I can see that Q is 0 right now and Q bar is 1. J and K and clock bar are 0, but the problem here is that they have been configured as outputs. I don't want them to be outputs. I actually need them to be inputs. So I'm going to change them to say switches of I can make them just 0 and 1. So push pull configuration, switch and switch and switch. So the names remain as is, but because those are inputs, I've configured them as push pull switches. So they can have a value of 0 or 1. JK clock clear. Okay, so let's see. My goal was to fill the table. So let's go down over here and look at the table. So the first entry in the table is if Q before pulse is 0. Right now, you see this, I have not gone through the pulse and Q is 0. So that's exactly what I need as the starting state. So that's good. I will leave that as is. I don't need to manipulate the Q to be a 1 for the first case. I wanted it to be a 0 and it is a 0, so I don't need to manipulate it. J and K are 0 and 1 respectively. So J is 0, which is good. K is a 1. So I'll make that 1. So notice when I changed K from 0 to 1, nothing changed. Because remember, the output of the flip-flop can only change soon after the negative edge of the clock. So it may have changed, it might not have changed, but it will have that option only after I go through the cycle of the clock. So let's see, Q after pulse is what I need to enter. Well, to write that column, I'm going to go up in the clock. So the positive edge of the clock goes up. And then once it comes down, that's the negative edge of the clock. So when I came back down, Q after pulse remains a 0 and Q bar after the pulse remains a 1. So I'm going to fill out a 0 for Q after pulse and 1 for Q bar after pulse for the first row. And that's sort of what we expected, because when J is 0, K is 1, we are in the kill state, so Q should be 0 and Q bar should be 1. Then that's exactly what we got. So that's how you would go through all these combinations. Let's do a few more. So now if you look at the second column, you need to first make Q before pulse a 1 and then set J as 0, K as 1 and then cycle through the clock to find the output. So the question is, and this is sort of the most interesting or the complex part of this experiment, is I need the Q before pulse to be a 1. Well, right now it is a 0. I want to make this a 1. So how do I do it? Um, one thing that we missed over here uh, was the conversation about clear. And we got lucky because we were in the reset state to begin with. But we can't ignore that anymore. So you see this, there is a clear input, pin number 13. We have connected clear bar to 0, which means if an input is active low, and if you connect it to low, that means it is active. So we have actually made clear bar 0, which means that I'm going to always be clearing this flip-flop. I don't want that. I actually want this to as a start state. That is fine. I can start there. However, I cannot leave it there anymore. So I actually have to make this into a 1 there, so that now I am not clearing the flip-flop. Okay, so I'm going to leave it there for now. And I'm going to go back to the table, and I'm now going to look at Q before pulse. I need to make that into a 1. Well, how do I make anything into a 1? Well, I have two options. The first option is go to the set state, make J0, make J1, make K0, go through the clock cycle, and Q will become 1. So that's one option. Another way to do this is to use the toggle state. And the reason why I can use that for now is Q right now before the pulse is 0. So if I go to the toggle state, use that, it will become a 1. So I can use either one. So let's see. Let's use the set state option. So I'm going to make K0 J1. And by the way, it doesn't matter how many times I change K and J over here, because the only thing that matters is what is the value of J and K when you have the negative edge in the clock. Only that matters. So I want it to be in the set state. J is 1, K is 0. So that's good. And I'm going to cycle through the clock to get my output Q to be a 1. And I'm not clearing the flip-flop, so that's good. Go up, go down, and I have Q to be a 1 in this case. So I've used the set state to make Q1. I'm going to go down here and look at what I need. So if Q before pulse is a 1, which it is right now, I need to make J0 K1. So J0 K1, cycle through the clock to find the output. And as we know, we are in the reset state here, or the kill state over here. So my Q, I expect that to become a 0 and Q bar to become a 1. Let's see if that happens. Go up in the clock, then come down in the clock, then Q has become 0 because we were in the reset state. And this is going to continue. We are going to keep doing this uh, for the entire table and get those values. Questions about this particular experiment? The best thing about this particular experiment is we already know the answer. I just need to go through and explore all the details. But I hope with the lectures that you have been uh, listening to me talk so much about JK flip-flop, you already know how to fill this table. We are just trying to see if it actually is true or not. When clear is low, it will set Q to 0. Yes, absolutely. But the key here is it will do that only at the negative clock edge. So for example, if I want to clear it at any time, I can only do that with asynchronous flip-flops, which this is not. This is a synchronous flip-flop. So let's see what happens. I will try to make Q1 first. How do I do that? Well, earlier I used the toggles. I used the set state. So let's now, for fun, uh, keep the clear bar 1, go to the toggle state and cycle through the clock, and I've made Q 1. And if Q is 1 and I activate clear by making it 0, oh, it is actually a asynchronous flip-flop. So the moment I made clear 0, it went to a 0. So this looks like 74107 doesn't wait for the clock edge to clear. It just it is not synchronous with respect to the input. So yes, the answer is if you make clear bar that particular input low, it will clear the flip-flop and make the output 0. But I don't want that to happen because you see several times I want that to be to respond. I need this to that input can be used to force the output to a low. I don't want that. So I'm going to uh, make that inactive, or I'm going to make that clear bar a 1 and then cycle through all the states. So for example, if I wanted the third row here, Q before pulse is 0, which it is right now, and I need J to be a 1, K to be a 0. So that's a set state. I already know what I should expect for Q. It should be set to 1. And I can see that only when I go up and come down. It sets it. All right, other questions. Um, so, for now, going through all these 8 possibilities is just going to be repetitive. There's not the key over here is to understand what Q before pulse and Q after pulse, what is the difference between them, and what I need to do to get the Q before pulse set up correctly. So that's the key in this experiment, and I hope I've shown you a couple of options to get the Q before pulse set up correctly. You can use clear, you can use set, you can use reset, you can use toggle. So you can use any option for the state of the flip-flop to set up the Q before pulse, change the inputs, and then cycle through the clock. All right. So the remaining things um, I'm going to do them separately. It's redundant for me to do all 8. But I hope you guys have seen and understood how we do this. The question online is, will a sign decrease satisfy the clock signal? Will a sign decrease satisfy the clock? I'm not sure uh, what you mean by that. Are you talking about a sinusoidal clock signal? So the clock signal, J signal, K signal, all these inputs and outputs, these are all digital signals. So they have binary, they should have a binary nature. So you should go up and down, uh, so low and high states, depending on uh, the, the, the cutoffs for a low and cutoffs for a high. So it's going to not respond to a sine wave the same way it responds to a square wave. It is probably going to select some voltage input to be a low, and there is going to be a lot of time where it is going to be in the undefined region of the voltage input. So it's not going to give you a reliable behavior. Willis, I hope, George, that was your question. And if I misunderstood your question, please clarify. Okay. Let's see. The next item on the agenda is going to be something slightly different. So what I'll do is um, leave this and stop the recording